at the end of the tunnel, right? Very good. So I just wanted to inform you that yesterday when you were taking the evaluation, I was at a campus about half an hour from here. This is Assam University, the Central University. And so you may be thinking this is very unfair. While you are taking an exam, I am enjoying time at another campus. But it was for a seminar. And the reason I bring this up is what happened is as the seminar began, there was a power cut. And then I realized that you and me, we are so lucky that we are in a room where whenever there's a power cut, we sometimes don't even know that the generator kicks in and the air conditioning is working all right there. There's no such thing as a backup generator. So if you have a power cut, that's it. Okay, so today we will look at resource recovery, and today's recovery will be of a precious metal. And over these two sessions, that means now and the next one, we will go over the factors that are important in this kind of a recovery. So the idea basically is you try to recover silver from a wastewater, and in this case, the main background that we have is of a laundry wastewater or laundry wash water. So what happens is we do have nanoparticles of silver which are intentionally, deliberately impregnated in many, many textile fabrics. And why so? Because it so happens that silver is a very good microbicide, and it also acts as a deodorant. It has some deodorant properties. So, especially in socks and undergarments, the manufacturers, they put silver nanoparticles in the textile fabric. But as you can see, it's again a mass transfer kind of an issue. You put these silver nanoparticles in, let's say, your socks. Fine. Now, when you launder them, when you put these socks in a washing machine, then this pair of socks is now it has contact with your laundry detergent, the detergent, and many a time what happens is that because of this chemistry between the detergent and the nanoparticle, the silver nanoparticles do come out of the textile. And so our approach was, well, as the wastewater or the wash water comes out of the laundering machine, can we, in the same way as we described for nitrogen or phosphorus, or heavy metals can be then put in the cartridge, and that cartridge would selectively remove the silver. Now, again, this is selective separation because, as you can imagine, the laundry detergent is a very complicated solution, and we'll go over the components and constituents of that. So, amidst that background, silver concentration is very low because silver is, first of all, not supposed to be there. So, again, it's a challenging separation problem because you are trying to remove something which is at a very low concentration, in this case silver, which is against a background where some other cations and some other components are at much higher, detergent constituents are at much higher concentration. So if you successfully do the selective separation, then can you recover? That's what this course is all about, recovery. And the idea here is you pass a regenerant, and that regenerant will strip out the silver from this column. And then how do you recover? There are two final products that we will go through. One is silver sulfide, AgQS, and that is the easier method. But AgQS is not a very prized industrial silver kind of a new product. So our next attempt, which will be the one that I will discuss more extensively, that is recovery as silver nanoparticle, Ag0. Ag0 has many applications in industry. Ag0's price on a per unit mass basis is much higher than AgQS. So if we can generate Ag0, uniform Ag0 nanoparticles, then we are in business. So that's the background, okay? So many people, they ask us, why are you even looking at silver? Silver is not really a problem. But if you look at the data, you will be convinced, I hope, that yes, there is an urgent need for silver removal because the use of silver-coated textiles has been rising and rising very fast. So, as you can see here, if I'm looking at typical precious metals or even heavy metals that we see in typical backgrounds, silver by far is much higher than some of the others. And if you look at the number of products of silver is again much higher. So the use of silver in textiles has been rising, and projections are it will continue to rise because our demand for these kinds of textiles, which have this microbicide property and deodorant property, that is rising as you can imagine. And it's not a small number. So this is the best data that we have, that is 2000, still pretty dated, but in 2000 the production of silver was 100,000 tons. So you can imagine it's not a minute quantity that we are talking about. And the annual growth rate, according to this reference, was 15%. So you can see 15% if you compound it over at least 18 years since 2000, it is a huge number and will continue to grow. And out of this is silver, the total silver, if you would like to think of it. Nanoparticles of silver, we are looking at 320 tons 7 years ago. Now, the question for us is not really how much nanoparticles of silver were produced. The question is how much of it is loaded onto textiles. And this is where things become very nebulous because the amount of loading has a huge range. So if you look at these references, we are looking at 1 milligram per kilogram. So 1 kilogram of textile has 1 milligram of silver, to 1 kilogram of textile has 21 grams of silver. So it's a huge range. Why is it a huge range? Because you can imagine the highest need for silver in textiles is in sporting apparel. and sporting apparel has much higher. And because silver, as we know, is a precious metal, price is also significant. So if you put a lot of silver, then the price of the textile rises, and only a few people can afford. So some of them put very little silver. So what I'm trying to say is it's something you don't have any control over. The textile that you buy for other reasons. You don't really buy for the silver component in it. But when you're trying to recover the silver, these things play an important role. That's all I'm trying to say. Okay. Now, how is the silver speciation? Well, what typically happens is that we start with some silver salt, let's say silver nitrate, and as you can see here, or we start with nanoparticles of Ag0, and then if it is AgNO3, as you know, it will dissociate to give you Ag plus. If it is Ag0, and if it becomes an oxidizing environment, then Ag0 would be oxidized to Ag plus. And then we can have a number of processes going on in parallel, and the end products of all this could be Ag plus, Ag0, or Ag complexes. So we need to come up with a technology that is robust enough to tackle all of these, because again, you don't have any control over this speciation. And so the speciation and quantity would depend on how much silver was loaded on the fabric and in what form, what kind of detergent composition you have, what is the wash solution chemistry. And as you know, in washing machine, you can have what we call in the United States hot or warm or cold wash. So the temperature also plays a role. And in the laundry machine, you run different cycles, the water fill cycle, then the wash cycle, then the rinse cycle. So the RPM at which this contact is made between the solution and the fabric or the textile, that also plays a role. Because again, it's a mass transfer. So the best estimates that we have are from this reference, 2010, that per person, we have about 0.5 milligram of silver per day that can be potentially used. And this is, of course, USD. So all I'm trying to say is, again, in the context of all our discussion over the last 4 or 5 days, amounts may be very low, but now you have to multiply it with number of uses. And in this case, when you multiply it with the number of washing cycles every day, that becomes a significant. So the question is, what is the need to recover silver? And the answers are manifold. There are all kinds of needs for silver recovery, because if you do not, if you discharge silver contaminated wastewater into the environment, you have all kinds of problems. What kind? You can have ecological problems. We know that silver is a microbicide. That's why it's put into the fabric. So if it is released into a water receiving body, then it could be toxic to the bacteria. It could impact the microbial balance, the algae, aquatic organisms, and also human cells. And especially what happens with wastewater treatment plants is that wastewater treatment plants, they rely, the secondary, the activated sludge or the trickling filter, it relies on very efficient performance by the microbes. Now, if you have silver in your input water, these microbes which are doing the main job for you, they might be affected. So you need to protect your process, your wastewater treatment, secondary treatment process from this. And as happens with many contaminants, the contaminants do end up to concentrate or So if you have silver in the water, it might be at a very, very low concentration. But as it moves up through the food chain, whether in the form of small fish to big fish to what you eat, or in the form of agricultural produce, that could become significant. And how do you get silver? You mine silver, and mining silver, of course, as with any kind of mining operation, it leads to greenhouse gas emissions. So that's an indirect uh, ecological concern, in the sense that if you can recover silver, your need for silver mining would reduce. That's the idea. So here you see silver ions. How do they affect a microbial species? And we know that silver ions do have the capability of penetrating or breaking through this cell wall. I mean, in a microbial cell, the eukaryotic cell especially, the cell wall is the biggest defense mechanism. So then they can, once they enter through the cell wall, then eventually they land up in the DNA. They have the capacity to penetrate through the cell wall to reach the DNA, and once it reaches the DNA, as we know, silver can this the helix can be separated into strands, and that's how the the, the process kind of gives rise to inactivation or killing of the bacteria. So now we also know that silver can affect the embryo. So what I have here is normal embryo of zebrafish, and what people have done in terms of research is the zebrafish eggs were taken to a plate, and silver nanoparticles at different concentrations were then introduced into the system, and what we see are malformed embryos or dead embryos, which again confirms that silver does have this property of, if not killing of microbes, definitely inactivation. And not only at the microbial cell level, but also at embryo level. And if you ingest a lot of silver in, let's say, your water or in your diet, then it leads to something called argyria, where it's called the blue skin syndrome. So your skin turns bluish, and you see here a case where a person with argyria is being interviewed. So the bottom line of this slide is you do have to spend efforts in recovering silver. Now, it so happens, because again, silver is a precious metal, semi-precious or precious, that its potential for recovery, economic potential, is the highest. So if you look at this, these competitors, silver compared to gold, compared to iron, compared to phosphorus, its economic value based on what is its concentration that we get in the wastewater, the economic value of silver is the highest. So the idea being that if you have to recover only one contaminant, the prime candidate would be silver, because just of its economic impact. And the other associated part is that in silver, there has been a slowdown in global production. Again, this is related to mining. Whenever you have an ore, you have some reserves that are very easily exploitable. And then when you run out of that, you have to then spend much more energy and effort from other sources, other ores. And so that's what reports are that that's what has happened to silver as well. The readily mineable silver has been now reached its capacity, and now we have to go to sources which have less silver or which require more effort. It's a critical material for clean energy use, recovery most commercially lucrative, and of course our aim is for a sustainable process. So unless you can complete the circle, uh, it will not be sustainable. So from a sustainability perspective, you do have to think of recovering the circle. Now, silver recovery is not really new in the sense that we were the first ones to do it. No. I mean, if you look at typical sources of industrial silver, they typically come in jewelry wastewater, electroplating wastewater. So industries have come up with very standard processes. The only difference is that they are working on silver at a much higher concentration. So there is this process called electrowinning, very commonplace process. What do? They bring silver in contact with cyanide, and what happens is that you form sodium argentocyanide. As you know, silver's Latin name is argentum, Ag. That's where the Ag comes from. So if you contact it with sodium cyanide, you form sodium argentocyanide, and sodium argentocyanide then can be exchanged, electrolytically exchanged with something like zinc, where you're sacrificing zinc. And what happens is, again, we will not get into the chemistry of this because this is not something we are doing really. I'm just trying to show you what some other alternatives are possible. So you sacrifice zinc, zinc takes place of silver, and you get silver, which is the silver that you're recovering. Okay. So that is electrowinning, but again, we can't apply this process to laundry water because of the concentrations. And as you can imagine, you're dealing with a very toxic sodium cyanide. Cyanides are very toxic, so you have to think of alternatives. Then there is another process called photoreduction, and as the name itself suggests, you hit silver with photon, H nu, and what happens is that you hit silver with the right wavelength, silver plus, Ag plus is reduced to silver 0, and silver 0, of course, now it is a nanoparticle, so it has this propensity to form these nanoclusters, and then these nanoclusters then aggregate to form bigger nanoparticles, and those nanoparticles that you can harvest. So photoreduction is pretty mature technology, but again, not really suitable for what we are trying to achieve. And what kinds of other processes are possible? Well, you can look at precipitating silver, and as you see, when you try to precipitate silver, your best bet is silver sulfide. But keep in mind, we are dealing not just with the pure silver solution. So it is very possible that in order to precipitate silver, you are precipitating many other compounds, and that from that matrix then recovering silver will again become a very challenging proposition. So the process, as you can well imagine now, because we have been spending 4 days, is an ion exchange process. So in an ion exchange process, we are exchanging silver with something else. And so why ion exchange? Because we know, as we were discussing in the context of heavy metal recovery, we know that sulfur is a very good material to look at binding with a heavy metal like silver. So it is very selective. We can get very selective ion exchange resins, and we have used sulfur-based resin, and it is very scalable. Ion exchange technology, I mean, from all the background knowledge that is needed to scale up very fast, very easily. In other words, if you tell me that in the lab you did this and the results are satisfactory, scaling it up is no problem because we have done this for other applications of ion exchange so many times that we know. For example, what would be the column size, what would be the column loading rate, those kinds of issues, very easily done. And the perception is that ion exchange is a very expensive technology. But if you look at, again, if you do a life cycle analysis, which is what one should do, because unless you look at the whole cost, you can't just make a conclusion. So if you look at if you do a life cycle analysis, you will be convinced. I mean, unfortunately, we don't have the time to do that, but many other people have done that, not necessarily for silver, for laundry wash water, but in general. And we see that it's very economically competitive. And the best thing about ion exchange is that its maintenance cost is very low, because when the column is running in the exhaustion mode, there's nothing you have to do. Only thing is, when it is exhausted, you need to regenerate it. So the industrial scale ion exchange applications, their maintenance requirements are very low compared to, let's say, a biological process. If you're looking at a microbial process, maintenance operation is very much hands-on throughout the time, because microbes do have this tendency to be affected by any disturbance in the process. But here, that's not the case. And for us, perhaps the most important from a sustainability perspective is that we can reuse the ion exchanger multiple times. Question was asked yesterday, how many times can you practically use or reuse a resin over how many cycles? And the answer is we routinely use resins over hundreds of cycles without any compromise in efficiency. All right. So, what are the challenges? The number one, as I said, is that silver, its concentration is very low in the wash water. Typically, it's in the range of 1 to 3 milligrams per liter. And it is against a background of detergent components, which are at a much higher concentration. Now, what we have to be very careful with is that this detergent matrix, and detergent is not just one compound, I will show you. It is at least dozens of compounds. So, any particular component of this detergent, would it interact with silver? One has to find that out a priori, as we say in Latin, before we start thinking of the process. Will there be competition? Yes, but that is not a big factor, because, as I said, we can make very silver selective resins. Then the question is fouling, because we are dealing with wash water, which has a lot of organics as well. Is there a question of fouling? And when we get this silver, what is its concentration? As I said, the concentration can vary, but more important than the concentration is the speciation. What is the silver? What form is the silver? And these competing cations may screen silver from the test. So our objectives were to try to recover silver against the competing cations and the detergent matrix as silver nanoparticles. As I said, we will talk both about silver sulfide and nanoparticles, but I would focus more on nanoparticles because that is a better answer to the problem. How can you establish an operating environment? And I would have loved to do a full-scale design, not full-scale, at least basic design, but unfortunately we don't have the time. But I hope by the end of these 2 lectures, you will be able to do that yourself, because all the data that you need will be available in terms of selectivity, And are you able to demonstrate that you are reusing and recycling the material? Reusing the regenerant, for example, recycling the ion exchanger. So the methodology again has very striking resemblance to what we have been discussing in terms of nitrogen and phosphorus. We have a cartridge, and into this cartridge we bring in the solution. As I said, the solution typically, the competing cations would be sodium, calcium, magnesium, and acid through this fixed bed. And in the fixed bed, you would get selective silver separation or removal. And what you would get out from this cartridge is a silver-free solution. And when it is exhausted, you put in a regenerant. And the regenerant that we settled upon after many candidates was thiourea. And I'll go through the thiourea chemistry with you. The thiourea, acidified thiourea. And then to this acidified thiourea, if you now raise the pH, you can get silver sulfide or silver nanoparticle. And that silver nanoparticle will be used. So this thiourea is being reused because we are stripping out the silver from it. And this silver-free effluent is the one that if you are on a sewer system, gets into the sewer system, but now it does not have any silver. If you have a septic tank, it goes into the septic tank. And especially with septic tanks, I think this technology is much more important because if you have your laundry water going into the septic tank, which has whatever, 5 milligram per liter of silver, that may impact your microbes, which are doing the kind of partial anaerobic digestion in the septic tank. The septic tank, as you know, it is septic, means it's an anaerobic environment. What is happening is that the solids that settle to the bottom, they are then acted upon by anaerobic microbes. And now if you have silver, those microbes, especially the methanogens, their biokinetics may be compromised. So the point being that we need to think of all these ramifications. Okay, so the approach is you make this fixed bed column, and then you have to put in, you have to know that if my silver concentration in the effluent is, let's say, 1 milligram per liter, 3 milligrams per liter, what is the bed volumes to break through? And once you know that, you have to then come up with, now if it's at a residential level, then you have to have some kind of a sensor, because how would the homeowner know that this cartridge needs to be changed? So our idea right now, it's not implemented yet, the idea still in the lab phase, is that you will buy this kind of a cartridge from the store, from a hardware store, let's say. You install it, it comes with a sensor. When the sensor kicks on, when it tells you that it is nearing exhaustion, you just remove this cartridge and replace it with a new cartridge. You bring this used cartridge again back to the hardware store from where you bought this, and the hardware store will then send it to a central regeneration facility where it will be regenerated and then sent back to the store. So that's the idea. That means as a homeowner or as a commercial, I don't know how much it is now in India, but in the United States, we have these commercial laundry places where you go and you do your laundry and you come back. I'm told that this has now started to pick up in major cities. One of my friend's friend is running something like this in Bangalore, just opened a startup. But it's not so much yet established business in India, but it's picking up. So it is a much better technology to use in a commercial laundry because, number one, you are generating much more wash water and your economics are much more favorable because you tie this one cartridge to a number of machines, and that gives you an efficiency in terms of Anyway, leaving that aside, so what do you have to do to design this column? You need to know the equilibrium capacity, you need to know the separation factor, you need to know the isothermal constants, you need to know the kinetic constant. Kinetic constant is very critical because what may happen and what we have seen, what does happen, is that the laundry wash water flow rate, I mean, you run a laundry machine, let's say once every day or 3 times a week or whatever. So when you run it, when you stack your clothes until you get a reasonable mass of clothes which need to be laundered. Now, when this laundry machine is running, it will spit out typically 3 times a wash water. One is this first run, which is the wash water that comes in contact with the detergent. Then it is the rinse cycle, so things like that. So the point being that when the laundry machine sends this wash water, the flow rate is very, very high, but it is a very short burst. So what you may have to do, that I admit will complicate the process, but what you may have to do is put in some kind of a tank where you can store this burst, and then if need be, you may have to send more than once. But anyway, so that we will come to the kinetics part a little later. Then the regeneration chemistry. Is there fouling? If so, how to avoid it? And most importantly, perhaps from the sustainability and resource recovery paradigm is how do you recover the silver nanoparticles? And can you reuse this regenerant? Can you reuse the resin? And as I said, reuse the resin is very commonplace. So there's not much that one has to do in terms of research. In terms of research, this. These are the most needed research areas. Questions? Okay. So this is the resin that we use. It's a commercial resin. It goes by this name, Ampersep GT74. As you can see, it's a thiol functionality. This is the sulfur that then binds to the silver. This is a very standard resin, so it's no more costly than your other, let's say, aminodiacetate or aminophosphonate or carboxylate. Oh, by the way, I just wanted to mention in passing, this resin, it's a very widely used resin commercially. Most of its use is not in recovering silver, but in recovering mercury. As you know, silver and mercury chemistry, they have a lot of similarity. And mercury recovery, this resin has been used for a longer time than for silver. But again, it is perfect fit for us in terms of silver recovery as well. So what happens is you get the silver, you get this resin in what is known as the acid form, the H+ form. You then preload it with sodium. You carry out an exchange. You flood this resin with a very high sodium chloride concentration and the sides of H+, and you raise the pH, so the H+ comes out easily. It then is in silver form. And then, in sodium form, and then the sodium form resin, you bring it in contact with the silver, and you will get a silver-sodium exchange because the resin prefers silver much over sodium, so it will then be loaded with Ag+, and when it is exhausted, you bring in thiourea. This is thiourea. Instead of oxygen, if you had this oxygen, it will be normal urea. So instead of oxygen, you have sulfur. So then it becomes thio. Thio means sulfur, thiourea. And this iodine, I will go over the chemistry. It is a very strong ligand for silver, and it has the capacity to take out the silver from this sulfur. So this is sulfur, this is sulfur. Why is this stronger? And over the last 4 days, our discussion, I'm sure, will give you some pointers. So you get this resin, because this is acidified iourea, so there is a lot of H plus in the system. So the resin comes back to an H plus form, and you get acidified iourea. Now the thing to note, and I will discuss this in much more detail later on, is that you form silver iourea complexes, and those complexes could be silver to iourea from 1:1 to 1:4. So AgTu1 plus AgTu2 plus AgTu3 plus AgTu4 plus. You can have all of these in your regenerant. Why is this important? It is important because they have different propensity in terms of, let's say, precipitating in the resin or being able to redeposit silver. So it's very interesting, but also complicated chemistry, and I'll go through the basics of that a little later. Right. So then the question is, how do you recover the silver? And as I said, we take in the regenerant, and that regenerant, the acidified iourea, is able to take out the silver, and then we do a electrolytic process. So we put this in an electrolytic cell, and what happens in an electrolytic cell, as you know from fundamentals of electrochemistry, is that you get an anode and a cathode, and the anode is a very oxidizing atmosphere, and the cathode is a very reducing atmosphere. So you force Ag plus to move from the anode to the cathode, where it is reduced to Ag0 and deposit it on the cathode plate. And then you take this plate and then you stabilize this, and then again the two-step process. Then you make this plate the anode, so that now in the next electrolytic cell, the silver comes out, but it is stabilized. It is stabilized in a citric acid solution, because once the silver comes out, they have this tendency to aggregate, and you don't want that to happen in your electrolytic cell. So you need to prevent aggregation. And then once you are ready for aggregation, the citric acid is very easily oxidized or removed. Once you remove the citric acid, or any stabilizer for that matter, we have looked at a bunch of stabilizers. Citric acid happens to be the cheapest and the best. Then silver nanoparticles are generated, which you can then sell or reuse or whatever. That's the idea. So we will look at the role of competing cations, regeneration, detergent chemistry, fouling, recovery, and reuse. So the competing cations. So we take a GD73 ampersand GD73 column, we load it in the sodium form, and we then run a solution where we had silver at 5 milligrams per liter Ag plus, sodium at 120, calcium at 60, magnesium at 10. These are the typical common competing cations that you find. And you then start passing the solution, and you look for breakthrough. And so what you see here is that sodium, this is the case where sodium broke through almost immediately, as you will expect. The thiol group resin has no affinity for sodium. Sodium breaks through. After that, we get magnesium, and almost simultaneously magnesium and calcium. But they break through very, very fast. Within a few within 10 bed volumes, whereas silver is non-detect for almost 20,000 bed volumes. So you see now the difference between our discussion in terms of line of pillow light or ammonium removal and hydrated granular oxide polymerase ligand exchangers for phosphorus removal. There, the exhaustion was typically less than 1,000 bed volume. Here, because the resin is so selective that we are looking at 20,000 bed volumes. Okay, and that is essential because unless you have a resin which is so selective, your economics will not be favorable. Okay. So silver breaks through at 20,000, whereas these break through within 10 bed volumes. Other cations, I mean. And what is the capacity? About 300 milligrams silver per gram of dry resin. So when we tell resin capacity, we always look at milliequivalents or milligrams per unit dry granular. And this selectivity for silver actually comes from the silver-sulfur complexation within the resin. Right, so then you try to look at the equilibrium properties and you do batch isotherms and you then try to fit the standard models. So when we ran batch isotherms and we tried to fit Langmuir model as well as the Freundlich model, what we saw is that R square for Langmuir is much lower than R square for Freundlich, which suggests that this is not a monolayer exchange. And when we do nonlinear fit, we also have some other coefficients which I will not get into. But this equilibrium model, the Freundlich model, gave us capacity of very close to 300, which is what, as I say, this is what we got from the column run as well. So column run, as you know, is completely different from a batch isotherm. Once they converge to capacity, that means not only that your resin is very selective, but that you do not have any kinetic limitations. So column, it is possible. It is possible that you have a resin which has a capacity of 300 milligrams of silver per gram of dry resin when you are doing a batch isotherm. But when you run it into a column, the column is taking up 200 milligrams. Why? Because there could be some kinetic limitation. Here, we don't see that. So for kinetic limitations, of course, the EBCT is very important. In our case, it was 3 minutes. And what we also observed was that this ion exchange is heterogeneous. That means we are looking at silver Na plus, silver H plus going on in parallel. And that complicates the system because when you want to run isotherms, you want to run binary isotherms. But you cannot really control. And in this case, we did see that because it's a ternary exchange, Ag plus, Na plus, H plus, the system becomes much more complex. And so, as I said already, this is not restricted to monolayer exchange. That we can establish very easily with just the isotherm trips. And then you do the same separation factor things as we discussed earlier. So in this case, what is interesting is when we thought we ran binary isotherms, we got a silver and alpha, that is separation factor for silver over sodium in the range of 3 to 6. But if you look at column, sodium breaks through immediately, let's say less than 100 bed volume, silver breaks through 2000. So column data does not support us separation factor of 3 to 6. If indeed that had happened, that the separation factor was 3 to 6, silver would break much, much earlier. So the point that I'm trying to make is that sometimes when we run isotherms, we always want that isotherm to be a binary system, but we don't really have much control here. So the system was a ternary system. So this is a distortion. This is not something that is defensible, this data. Okay. And further, we noticed that whenever we were running these systems, there was always a pH drop, which means that there was H plus playing a major role. So it's a ternary exchange, and this separation factor is not what you will find in a column. And this is all the data which I will not get into. So then we come to kinetics, and whenever you come to kinetics, you have to first of all see what is the rate limiting model. And there are two ways of doing it. One way is literature suggests that this would be the rate limiting model, the rate limiting step. But in our case, because our background solution was so complicated, we couldn't really rely. So what we had to do was the hard route. Hard route is you try out different models, the most commonly accepted models, and then see which one fits the best. So we tried out a number of them: zero order, first order, pseudo first order, pseudo second order, and interparticle diffusion. And then we tried to see, based on the MATLAB code, which one gave us the best R square, and this one. And it's not surprising, really, that interparticle diffusion gave us the best fit. So this curve fitting shows that interparticle diffusion is the best model that describes the uptake kinetics. And the concentration gradient in the resin phase, again, as we have discussed in the past, what happens is if you have a resin bead, then what is the flux curve that you get? The flux curve that you get is that outside the resin, the silver, excuse me, my apologies for this disruption. So, as I was saying, you have a certain silver concentration outside the resin, and the driving force is the flux within the resin. And of course, when you look at a standard model, you would say that this flux curve extends all the way to the center of the resin. But as you know, it never really happens like that. I mean, most of the time, the flux curve would look something like this. That means it ends at some distance. It ends some distance away from the center. That, in other words, it means that there is a part of this sphere where silver cannot really reach, very close to the center. But anyway, that is just something that may impact your I mean, when we do a kinetic model, what is our goal? Our goal is to come up with a diffusion coefficient. And that diffusion coefficient is diffusion of silver inside the resin. Now, when we model that, then we think that this is a homogeneous model. That means the diffusion of silver inside the resin is the same, and that is based on the R. So there are two ways to approach this. One way is you find out how much silver penetrates into your resin. How do you do that? You cut the resin, you microtome it, you put it in a, in that microtome resin, the encasing resin. That's a different resin. That's not this one. And then you take it to an SEM, or it's basically TEM. And in TEM, if you have an EDS with the TEM will tell you where it meets copper or silver and where it does not. But it's not really very important, because we can say that the effective diffusion coefficient is based on whatever diameter or radius that we have. And that is good enough, because that number can then be put into any model. So we don't really have to do all the detailed analysis to see where the flux curve ends. Because if you base it on this diameter, that will be, you can say it's a pseudo diffusion coefficient. So this is pseudo diffusion coefficient. And this is, you can say, true. And so if you want to say true, then you absolutely have to know. But if it is pseudo, then it doesn't really matter, because you're just basing it on the radius or diameter that you have for the resin. And all I'm trying to say is that in engineering, we are all engineers. In engineering, we try to come up with parameters that give us the maximum applicability. So this, even though the word is pseudo, it is much more useful, because I can apply it anywhere. This one, I need to look at every possible size of a resin, within that size where it ends. So it's not very helpful, really speaking. But if you're a chemist, then you would be much more interested in this, because you want to know where the diffusional resistance comes from, how strong is it, so forth and so forth. So we do have a little different perspective. From an engineering perspective, one diffusion coefficient that you get for the radius, even if it is a pseudo, it's much more useful. That's all I'm trying to say. And as you know, when we do kinetic tests, then this interruption test is very common to confirm that indeed if interparticle diffusion is the rate limiting step. So what happens is, as you saw in an earlier slide on day 2, and I'll just redraw it. So if I'm looking at bed volumes versus concentration, and I have a column, I have a resin in the column, and I'm feeding a solution, and I'm looking at them. So in this case, let's say this is silver breakthrough. So I'm running this column, and silver concentration now is so much. If I stop the column, and then I just let the column sit idle for some time, then you will see an immediate drop in concentration. And then when you restart the column, the concentration will pick up again. And again, when you stop it, if you stop it, you will see a drop. So there is a whole science behind it, which I will not get into. But all I'm saying is that interruption test is the best way to confirm if interparticle diffusion is the rate limiting step, because this kind of profile you will get only if intraparticle diffusion is the rate limiting step. Okay, so we just confirmed that. We tried out a bunch of models. Interparticle diffusion gave us the best fit. Then we did interruption tests to confirm if indeed that is the case.
And most of the time, interparticle diffusion is predominant or film diffusion?
Well, it's difficult to say. With chelating resins, it's typically intraparticle diffusion. But again, I would not like to generalize it. It does sometimes, it may sometimes be liquid film diffusion controlled as well, but those are by far, you can say, exceptions.
And sir, how we can identify it is a particle diffusion? Sorry, film diffusion.
Well, the way to do that is you have a reactor where you manipulate the stirring speed. And so what typically happens is that when the stirring speed is very low, you get some diffusive, you get some kinetics. As you increase the stirring speed, the kinetics gets better until you come to a certain stirring speed, after which it does not change no matter how much higher you are going. That's what tells you that after this, it is interparticle diffusion. Until that, it is the liquid film.
Actually, sir, it means that during stirring, this film may break. No?
Well, this film is actually a fictitious film. It's not really a film that you can go and sample. It is a film which we use as a model so that we can get the mass transfer.
Is a liquid resistance?
Yes, the resistance is in the liquid phase. That's all it means. Yes, but there is no kind of real film actually. It only is what we use to understand this system. So that's why we say it's kind of impossible to find this film thickness. So what do we say? We say KLA. That means on a per unit time basis, what is the mass transfer coefficient? That's all. Questions? Any other questions? Yes.
Is there any low-cost approach? Any low-cost approach towards silver? Any
low-cost approach? I mean, you have to tell me what is the problem that you're trying to address. What is the silver concentration? What are its competitors?
Laundry. Domestic laundry.
Domestic laundry.
Any approach?
Domestic laundry, I don't think there is any, because, as I said, your silver concentration is so low to begin with, and it is against this background that what would be a possible competitor? Precipitation. For 1 milligram per liter, silver precipitation will just not, I think. And even if it worked, then recovering silver would be almost impossible, because you would have so many precipitates.
And sir, here INFC is suitable because the concentration is very low in aqueous phase. That's why it's not selective.
No. It's the resin's functional group which makes it selective. You need a selective one because its concentration is so low. If the concentration were high, then you don't need this kind. So ion exchange works best when the target ion is at a very low concentration, but then it is against a competition of other ions which much higher. If, for example, you have an industrial wastewater where silver is 300 milligrams per liter, then you wouldn't do this process, because your bed would get exhausted so fast that you would have to regenerate it so often. So, if let's say I'm just making a hypothetical situation, if it's just an Ag plus solution, yeah, then. And so what sometimes people have done in a very, very different context, but it may still be appropriate here to mention. You first run an RO, because what does RO do? RO concentrates, right? Because the reject now gets more concentrated. So you run an RO, you get more concentrated, and then you precipitate. That's very cool. But in this case, it will not work, because 1 milligrams per liter going into the RO, even if it's concentrated twice, it will be 2 milligrams. Okay, so let's stop here because it's right 11:15, and we will take a break. And when we come back, we will look at the other considerations that I talked about.
Sir,
Yes.
had this been film diffusion, wouldn't the point jump back to the original?
In film diffusion, this drop would not occur. It won't occur. Liquid film diffusion, there is no drop. That's it. That's what we use that information. Because if it's in the liquid film, topping the column is not going to give you any advantage. Yeah. Yeah. Any other question? Yes.
Like in India, for making different sweets, we use silver foils and all.
Yes, yes, yes.
Do you think this concept will work? Not a small scale, but on large scale.
To be very honest, I can't say without looking at the details of it. But, I mean, first reaction would be why not? Then one has to look in more detail. All I can say is that we have worked also with the wastewater from dentist offices. I mean, dentistry offices, as you know, do have this. So that works perfectly fine. Now, silver foil in sweets, I just don't know the chemistry. I just don't know how it is done. I mean, I enjoy the silver foil sweet, but pardon me?
It's silver particles in anywhere, come atmosphere, then we can.
Usually, after preparing everything, the foil is laid over the thing, whatever sweet we are preparing.
Yeah.
Now, there will definitely be a washing phase after you cycle or something at intervals. Like it happens in any.
Of course, yeah, yeah.
So,
But how a foil is made, what is the starting solution? I don't know. But it seems as if this would be a case where silver would not have much competition. Well, again, would this be the best possible technology? That's what I don't know. But if you can convince a sweet shop to fund you for some research in this area, I would be most happy to collaborate. Very good. So let's take. I mean, I don't think we have sweets with silver foil on them, but we can have sweet tea or sweet coffee. go back. So to conclude this part of the work, we can say that this ampersand resin, the thiol-based resin, the one that we use, it gives us the capacity of about, as I said, 300 milligrams of silver per dry gram, or which translates to 2.8 milliequivalents of silver per gram of the resin. It is very selective, as you saw. The silver breakthrough was close to 18,000 bed volumes, whereas sodium and calcium and magnesium, they broke through within 10 bed volumes. So the resin is selective, highly selective. And the mechanism of AG uptake is this complexation between the thiol group of the resin and silver. And the isotherm, Frontlich isotherm, it best describes this process. And this exchange is not binary, but kernel. And intraparticle diffusion model governs the rate. So now let's look at regeneration. So we regenerate with thiourea, and when we ran batch experiments, we saw that, as you can expect, that the concentration of thiourea plays a significant role in terms of how much you can regenerate. So, how much silver you can take out of the resin if your thiourea concentration is 0.1 moles, 0.2 moles. So, it follows this curve, and as I was saying, what is going on is that the resin comes into contact with thiourea, and the resin then goes back to the H plus form, and you get thiourea, Ag, thiourea complexes, but these complexes could be N, could be 1, could be 2, could be 3, could be 4. And so we saturated resins, we regenerated them in the batch mode with thiourea concentration anywhere from 0 to 0.5 moles. And based on this study, we selected 0.2 mole thiourea as our regenerator. And this is acidified thiourea. So the pH plays a very important role. And as you see here, as the H plus concentration increases, your percentage regeneration increases with thiourea at 0.1. So we studied pH 1 to 5 or 6, and not below 1, because pH below 1 is very difficult to work, as you can imagine. It can corrode your fixtures, it will provide this acid shock. So we selected the pH value of 1 for subsequent studies. And then when we started to regenerate, we used 0.2 mole thiourea at a pH of 1. And what we saw is that within the column, we got very heavy precipitate. And within 10 bed volumes, the column collapsed. Because as you know, the column is not supposed to get this high dose of solids. So you cannot allow actually precipitation inside the column. And we took this precipitate and we ran PDX, we ran XRD, and what we saw is that this precipitate is actually Ag2, Du6, SO4, 4H2O. And the bottom line is we have to prevent this formation of this. But the reason I put this slide is because when you get the precipitation in your column, you have to know what it is that you're precipitating. You cannot just base it on some guess, because this particular compound, nobody really has reported it. So unless we do detailed characterization, we can't know. So when when we carried out further regeneration studies, 0.1 molar thiourea at pH 1. So what we saw is that, of course, if you remember the lab setup, we have a solution that we are pumping into the column, and from the column we have a fraction collector, and the fraction collector is based on bed volumes, and then after a few bed volumes, the test tube moves. So what we saw is that from here to here, when we would get the effluent in the test tube, it would be fine, but immediately it would precipitate in the test tube, not in the column, but in the test tube. But as you can imagine, that's also not something very desirable. And that happened when we have, the silver concentration is rising, as you know, because when you're regenerating, you're getting more and more silver out. This was happening mainly when the silver concentration was greater than 1000 milligrams per liter. So, what do? You go back to your calculation, go back to the aqueous chemistry model. And what we found was that this silver, this precipitate was AgTU3. Okay? Because you know the binding constants, you can find the speciation. So AgTU3 plus, that means 3 molecules of thiourea for every ion of silver. That was the precipitate. And so once you are forming a precipitate in the test tube, then of course, as you can imagine, mass balance becomes almost impossible. So what we decided to do in subsequent protocols was to dilute the samples as they came out. So we didn't allow the precipitation to occur. We kind of, by design, we introduced more water so that the concentration could be depressed, just so that we could do out the mass balance, because at the end of it all, you have to do a mass balance. And once you form a precipitate, mass balance becomes almost impossible. So then I'm showing you now that we were able to firstly prevent the precipitation from happening in the column, and secondly from precipitation happening in the test tube of the fraction collector. Then we looked at a regeneration, and what you see is a little different from what we have seen in the past, in the sense that it's a very long tail, as you can see. You do get pretty decent climb of the curve, but then, of course, there are a few bumps here and there, but after when the effluent concentration on its downward trajectory is, let's say, 250 milligrams per liter or 200 milligrams per liter, after that, it's a very significant resistance to it coming out. So that means you have to go for a much longer bed volumes. But I do want to point out that the breakthrough was at 18,000 bed volumes. So compared to 18,000 bed volumes, 200 bed volumes is not a very high number. If it were the case, hypothetically speaking, that you are reaching breakthrough at, let's say, 800 bed volume, and you need 200 bed volume for regeneration, that would not be a good process. But because your breakthrough in the exhaustion mode is 18,000 bed volume, 200 bed volume for regeneration is not a bad number. Okay? And but 75% of the silver leached in the first 50 bed volume, and it took for the 20% more, it took 160 bed volume. So there's definitely a resistance here. And when we regenerated the resin, the next uptake cycle, we saw a black coating on the resin. And this was basically silver thiourea adsorption. So very interesting. What's going on actually So what's going on actually is that you put in thiourea, acidified thiourea, it takes out the silver, and then we get this speciation. And in that speciation, what happens is that silver in the AgTO2 plus form then reabsorbs on the resin. And that is very interesting chemistry. So of course one has to now look at it in more detail. So as I say here, TU2, AgTU2 plus was the dominant species and it was being reabsorbed, because of which you have this kind of profile. So what do? Well, you now try to establish, well, what percentage of your silver is in AgTU plus, 2 plus, 3 plus, and 4 plus. So if you have 0.1 molar thiourea as your regenerant, then as you see, when you're, of course, this is a function of the silver concentration. So as this concentration increases, you see so high a percentage of AgTU. Now, if this is your situation, then there's no wonder that this would become deadsorbed. So what do? You try out other scenarios. How about 0.2 molar? 0.2 molar thiourea, you are increasing the silver concentration. What you're now getting is percentage of AgTU2 plus is still rising very fast. So this is also not a good candidate. How about 0.4, 0.5 moles? And now you see, once you have 0.5 molar thiourea, you are able to what we call break the curve. So now it's a downward slope. This is upward, this is upward, now it's downward. So what that means is that if you have to regenerate and you do not allow the AgTU2 plus reabsorption, then you have to go in for a higher regenerant concentration. Not 0.1 molar or 0.2 molar thiourea, but 0.5 molar. So precipitation of AgTU3 plus and reabsorption, to prevent that, we have to go to 0.5 molar thiourea. And that was what we chose for subsequent regeneration, as it suppressed the fat fractions of AgTU3 plus and AgTU and increased AgTU4 plus. Is what you want. So the bottom line is, when we deal with the complexes in the regenerant, then we have to do a very careful speciation, because some of these complexes may be problematic, and in this case, we do see AgTU2 plus to be problematic in the sense that it reabsorbs. So now, if I have 0.5 molar thiourea plus 0.1 mole, because this is acidified, as you can see, it's a much better profile, because at least from 200 I have been able to come down to, let's say, 75 bed volume. There is still this tail, which is a very obstinate tail. It doesn't want to come back to the baseline. But at least it's much better than what we saw in the earlier slide. The precipitate was seen in sample 9 and 10, which was resolved. Dissolution at higher thiourea concentration suggests precipitation due to AgTU3 and 75 bed volumes for regeneration. Supports the hypothesis, and increases AgTU4 plus. So this is what you want. You want AgTU4 plus to be your dominant. And in order to do that, you need to get 2.5 molar per. All right. So in this part, what we can conclude is that, well, 0.5 molar thiourea at pH 1 is the best regenerant, and it gives us about 96% regeneration. It takes 75 bed volumes, but again, I cannot stress enough, 75 bed volumes may sound too high, but this is against a exhaustion breakthrough at 80,000 bed volumes. So we have to keep that in mind. And what happens is, we do have this tendency, the exchanger has this tendency to reabsorb AgTU2 plus, and we have to prevent that, of course. And we do see precipitation of AgTU3 plus, if I go for a lower strength regenerant, 0.1 mole or 0.2, because when the silver concentration rises more than 500 milligrams per liter, this precipitate starts to form. So I have to prevent both of these: precipitation of AgTU3 plus, deabsorption of AgTU2 plus. And the only way to do that is to go to AgTU4 plus. TU concentration of 0.5 mole per liter is chosen that keeps AgTU3 plus and AgTU2 plus fractions below 35%. And that is the one that we chose, 0.5 molar. So now we come to the detergent chemistry. Anyway, let's stop with questions. So, as you know, detergent is not just one compound. Detergent is a slew of many compounds. So, the first component, of course, of a detergent is a surfactant, as you can well imagine. And the common surfactants are this one: sodium dodecyl benzene sulfonate, sodium dodecyl sulfate, and perol. Perol is a trade name. So one of these you will find in 99% of the detergents that are available in the market. Then we have builders. Builders, they capture hardness in the water so that those ions are not able to interact with the detergent. So you have zeolites typically. You have you may have sodium bicarbonate. You may have sodium metasilicate pentahydrate, diethylene triamine sodium pentaacetate. These are the most common builders. You have, of course, the bleach, as you know. You do want to raise the pH. So common bleach solutions that are used are sodium perborate, tetrahydrate, and tetracetylethioamine diamine. Then you have something called soil anti-redeposition agent. So the idea is your clothes are soiled, and you put it in the machine, and you get the soil out of the textile. But there is always a tendency for this soil to redeposit. And in order to prevent that, you put soil anti-redeposition agent. And the most common one is cellulose-based sodium carboxymethyl cellulose. And then you use something called formulation aid. This is to build up your detergent, and the most common one being ethanol. And finally, you have an optical brightener, because that's what, when you see in the ads, this particular detergent gives you so white clothes, it's shining and all that. How do they do it? It's typically done through the introduction of a brightener. What is the most common brightener? 4,4' diamino, 2,2' still being disulfonic acid. Okay, so why do I put all of these? I put all of these just to show you how complicated the situation is. You have no control over the detergent, right? You just buy the detergent either in a powder form or solution form, and detergent company will not tell you what all they have. So you have to come up, if you want to introduce a process that can recover silver, you have to come up with a robust process that can take care of any of these constituents. That's the idea. All right, so this is a very dense slide, and my apologies for it, but I think the information that I want to show, it is needed. All these graphs are needed. So I will go very slowly, and please stop me at any time. So what is it that we are trying to show here? What we are trying to show here is that in the earlier slide, all these components that I talked about, what role do they play in silver recovery, or silver availability rather, I should say. So the question is, if you run an experiment and you put in detergent and you put in silver and you say, well, 70% silver was recovered, let's say. The question is, what component caused this 30% loss? You have to know that. So that's why we have to do very extensive experiments with each one of these components so that we can zone in as to which one of them is the problem. So let us do it one by one. SDBS. SDBS is sodium dodecyl benzene sulfonate. Okay, so it's a surfactant. And what is it that we are saying? That well, if you just had SDBS in solution, then we are looking at free Ag plus and total dissolved Ag. Okay, so what percentage of your total Ag is in free Ag plus form? That's what we want to know. Why? Because free Ag plus is what we need for the resin to work. Okay, so what we see is SDBS no problem because 100% of the Ag is in free Ag plus form. So then we come to, let's say, SDS. What is SDS? Sodium dodecyl sulfate. With SDS, the free Ag plus and the total dissolved Ag plus is total dissolved Ag is not much of a difference. Okay. So by doing each experiment, you then can say, well, which one of them has no problem? It is not a problem. So that is what I'm saying here. That free Ag plus which we determine by ion selective electrode and total Ag which we find by atomic absorption spectrometer, then they did not change in the presence of SDBS, SDS, payroll, carbonate, ethanol, CMC, and still. Okay, so with these components, there is no problem. Whatever silver we have, it is all present as Ag plus, no matter what their content. Okay. So then we come to, let's say these are the most problematic ones. The zeolite. You see that the free Ag plus, it drops so significantly. And why? It's not really very difficult because zeolite is an exchanger itself. And so now we have this competition. And so what's happening is that the zeolite is taking up all the Ag plus. Then let's look at DTPA. DTPA, again, the same problem. How is DTPA hindering the process? Well, it is chelating with Ag plus. But in DTPA, what happens is that if you add H plus, if you acidify the solution, you add H plus, the DTPA goes back to the unchelated form. So you have now kind of arrow in your quiver whereby if this detergent contains DTPA, what we can do is we can acidify the detergent solution, and that will then take care of this DTPA problem. If you're looking at perborate or TAED, then what that is doing is, because as you know, perborate is a very strong reducing agent. So what it is doing is it is reducing Ag plus to Ag0. How? Again, you have to go through the chemistry. I don't have the time, so I will just say that what is happening is HO2 minus is your active reducing agent. But this, again, we have a way to tackle this, and that is through pH. If you have a pH of 9.5, then you will get this Ag plus reduction to Ag0. But if your pH is acidic, pH 3 for example, you will not have any reduction. Why? Because once again, if you go through that chemistry, perborate chemistry, you will. So if you go to pH 3, free Ag signal remains steady. Okay. So what you see here is now that, well, I have a situation where I am looking at time and I see this very precipitous drop of silver concentration. But if I acidify, I can go back to the original AG concentration. So all of these, except for the zeolite, it's a reversible process in the sense that if it is affected by acidifying the solution, I can I can eliminate that effect. Zeolite is kind of an irreversible process. And so the question is, what do you do if you have a zeolite? So now let us look at performance of the resin. Again, this is a very dense slide, but rather than looking at each one of them, which we don't have much time for, let's look at the conclusions. And at the end, I will give you 3 publications that we had. So once you read these 3 publications, you will get all the details that you want. So the resin performance was unaffected, greater than 95%. If you had STBS, SDS, Barrel, metasilicate, carbonate, CNC ethanol. If you have zeolite, the resin removed 26% of the silver in the presence of zeolite. The Ag plus, the Ag was recovered from zeolite if you had to went to a pH 3. The resin with TTPA removed 25% of Ag. It was chelated with TTPA. But if you brought in calcium, the resin removed 94%. So if you have TTPA in your detergent matrix, you will have to add calcium so that the calcium ties up with the TTPA so that the silver is freely available. Okay? And this is very interesting because when we look at laundering, we always consider calcium to be a problem because calcium is the hardness. But here is just one solution, one situation where we are intentionally bringing in hardness in the form of calcium. If this detergent contains TTP, okay. So, and if you have a bleach, then the resin performance was compromised. But again, if I reduce the pH, if I raise the H plus concentration, the resin comes back to its original. Its performance is pretty good. Okay. So the bottom line for all this is that when you want to use this process, you have to acidify your influent solution because that will take care of most of these problems. Yes.
Resin may contain bivinyl benzene ring.
Yes, cross-linker.
And I think HDS starches also contain benzene ring. So when you pass the sample directly to this exchanger, HDS may get attached to the resin. So if performance after 2 or 3 cycles may be.
I will show you a little later what we call as fouling studies, and there we will look at this. So the answer is no. What you are saying, because SDS has a benzene structure and the divinyl benzene also has a cross-linker is there, they will have a hydrophobic interaction. Yes, but for it to be sorbed, you need much more delta. But I will show you results. Okay. So this was, as you see here on this graph, with the resin mass of 0.1 grams at pH 3, Ag plus being 5 milligrams per liter, and these other concentrations, T equals 0, T equals 15, T equals 24 hours with the bleach. Of course, the bleach brings in a very low. But if I acidify resin and bleach mass, I do get close to 98% of resin of Ag plus in the resin phase. Okay. Right. So, column exhaustion and regeneration. Well, we saw that it is about 80,000 bed volumes to break through. And so, what is the new column that we have? It has a detergent solution concentration of 2 grams per liter, very high. I mean, typically when you when you put your detergent level, whether it's a powder form or solution form, it is typically 1/4 of this. Why did we go for 4 times as much? Because we wanted to stress the system as much as possible. Have as much concentration of detergent components as possible. 1 gram resin in a column, 1 within EPCT, and now we find silver breakthrough in 8,800 bed volume. Earlier it was 18,000, but that 18,000 was a synthetic solution which had only silver and sodium and calcium and magnesium. Now, when we put it into the detergent solution, the 18,000 is reduced to 8,000. So, you see it breaks through much earlier. And when we regenerate it with 0.5 molar thiourea, then we have to go back to 150 bed volumes, because after this is a very pronounced tail, and we then have to again put in a fresh dose of regenerant. Again, it comes back to tail and again. So there are some additional resistances. So for this part, what we can say is that builders like zeolite, sodium metasilicate, ETPA, bleaching agents like sodium perborate, they do impact Ag+ availability in the detergent solution. And if that's so, then it will affect the performance. So the role of pH is very critical. And in certain cases, if we bring in Ca2+, then we can have a little betterment of process. So for all subsequent runs, we ran them at a pH of about 3.5, because we need that acidic environment. And the packed bed resin column broke through in about 9,000 bed volumes. So you would suspect there is fouling going on. So let's look at fouling. So how do you look at fouling? Well, you take a fresh resin, take a resin that you have already exhausted, and you do an elemental scan. What we see in the elemental scan is that the shells of the fresh resin versus the shells of the detergent contacted resin. In the fresh resin, XPS confirms COS Na, of course. In the detergent, XPS confirms COS Na Ag, of course, and calcium. Carbon percentage changes slightly, very slightly, from 73 to 74% on contacting with the detergent. C to S ratio is 6.29 for fresh and 11 for detergent contacted, which suggests that carbonaceous matter did deposit on the resin surface. So then we look at bonding, and when we look at bonding, we found that fresh peak was 284.8 EV C1S, and detergent is 284. So not much of a change. In the case of detergent solution, the peak slightly shifted to 284, possibility of reduced oxidation state of C. But when you take all these things into consideration, there is no major change in carbon bonding. You do get a few pieces of data here and there, but overall, not a major thing. So there isn't much evidence to support fouling. Is that enough? Not really, because one has to do additional characterization. So you do EDX. You microtome your samples, and then you run an EDX on it. And what we find is that if it's a fresh resin, how much carbon? 71.89. If it is detergent solution contacted resin, 72.2. Now what we did is we said, well, if it is fouling or some kind of an effect of organic matter which is present in your laundry wash water, how about trying to make humic acid as the surrogate of organic matter, which is something we do all the time in environmental engineering. organic matter is such a broad category, so many compounds possible, that we typically then take humic acid and we see if this is something we see with humic acid, then we can say, well, yes, then there is this organic matter, the effect of organic matter. So humic acid is what we call a surrogate parameter. So we took a detergent solution and humic acid and contacted the resin with that, and then what do we see? 71, 72, 73, these are not major things. 26, 25, 80, that is much reduced. Sulfur also nothing major. And these are the three resin samples. One is just detergent, one is humic acid, one is detergent plus detergent solution contacted resin, fresh resin, that is 3, 2 is humic acid, 1 is detergent. And then we look at this relative percentages. And after all this, what one can say is that there is not much change, insignificant change observed in carbon composition between the resin. So, though we still do not have an answer to why 18,000 bed volumes came down to 9,000, it's not foul. Fouling means that it is a reversible process, that the resin sites are now blocked. That's not what we are seeing. So, yes.
You done your experience after how many cycles?
One. So then we try to do a column exhaustion run, fouling study, and what are the flow conditions? EBCD of 1 minute, cation concentration Kg plus is 5, Na plus is 325, Mg2 plus is 8, calcium is 54. Now we put humic acid and we put detergent 2 grams per liter, as I said, 4 times what we would normally see as the highest. And humic acid plus detergent compositions breakthrough and with just detergent. So the packed bed with humic acid in the detergent solution as the influent broke through in 8800 bed volumes. The packed bed with only detergent solution also broke through in 8800 bed volumes. The early breakthrough as compared to 80,000 is most likely not caused by any fouling. The role of so it says what we are suspecting, and at this time I don't have a definitive answer, is that it is the detergent components. What they are doing is that they are affecting the kinetic parameter more than the equilibrium or this fouling. Okay. So to conclude this part, yes, we do see some carbon deposit on the resin, but we cannot call it foul. Carbon bonding remain unchanged. EDX study reveals marginal increase in carbon contact, but it's only a marginal increase. It's not a substantial increase. EDX study did not show a drastic change in carbon content between outer and inner surface. As you know, the best way to do that is you look at this cross section, and as you move along from outer to inner, do you see much of a difference? No, we didn't. The packed bed column with humic acid and detergent solution broke through, silver broke through at the same number of bed volumes as with only detergent. And so there is little evidence of fouling. Impact is not considered to be significant. So now I would like to spend some time on this nanoparticle recovery. So nanoparticle recovery, as I said, the process is an electrolytic process, and we take this acidified thiourea and we put it in an electrolytic cell, and the silver moves to the cathode. It gets reduced at the cathode. Now this plate onto which we have silver 0 deposited, we then take to another electrolytic cell where it becomes the anode. And now when I apply electric current, all this silver comes out and that's what I have to capture. In order to capture, I need a stabilizer, and that in our case was citric acid. So AG recovery at 0.05 amperes. So in any electrolytic cell, what do? You keep looking at various parameters. Current, how much agitation you are providing to the system. And these are all at ambient temperature, so temperature didn't really play a role. So what you see here, you see three curves. Current is 0.03 amperes or 0.1 or 0.3. And you are looking at silver recovery. And you see that at around 300 RPM, you are getting, if your current is 0.05 ampere, you are getting about 91% silver recovery in the form of nanoparticles. Similarly, you are looking now keep in mind, I have said again and again that one of the benchmarks of this process is how much thiourea you can reuse and recycle. So, in an electrolytic cell, there is always a chance that the thiourea will be oxidized. So, we have to see how much of thiourea loss we are encountering. So, this graph shows you that if I run the system at 0.05 amperes and at 300 RPM, I lose only about 3% of the thiourea, which is very good. I mean, 3% loss is bearable, eminently bearable. So, current, then we look at agitation. So, percentage recovery at 0.05, this is 300, this is 600 RPM. So, the more agitation you provide, you can increase your silver recovery and you can decrease your thiourea loss. So, what that tells you basically is that we will run our electrolytic cell at 0.05 amperes and 600 RPM. So how do you optimize this? You have to come up with a reaction kinetic based model, and you then fit this model to these standard models to find the value of K, the transfer. And so what you first find is that the kinetics of electrodeposition is first order. The value of K tells us how fast or how slow this electrodeposition is. If you want to increase K, if you want to increase K, the increase of K with current at constant stirring speed shows that electron transfer at the cathode controls the electrodeposition. So, electrodeposition, the rate controlling steps could possibly be the H plus generation at the anode, or the passing or the movement of H plus through the system meaning between the two electrodes, or the electrode transfer. So here electron transfer at the cathode is the controlling step. At the beyond a current of 0.05 amperes and 300 RPM, there is not much significant change in K. This implies electron transfer constraint is overcome. Therefore, we chose 0.05 ampere to be the operating current. If I increase the stirring speed, K increases. Increasing K values with stirring speed at 0.05 ampere, it implies existence of mass transfer constraint in the system. Because higher the stirring, the more the K definitely means that there is a mass transfer constraint. But beyond 600 RPM, K does not change, indicating that the mass transfer constraints have been fully overcome at 600 RPM, and 0.05 ampere current, 600 RPM are determined as the optimum operating parameters. So then we look at the possible reactions in the electrolytic cell, and you have AGTU, X could be 1, could be 2, could be 3, could be 4, as we just said, and it is coming into contact with an electron, so the Ag is reduced from Ag plus 1 to Ag0. And the TU is, it's dissociation reaction followed by reduction. Reduction followed by dissociation. So one has to look at the electron volts and all that. And as you know, in an electrolytic cell, there is always this possibility of hydrogen generation. So, and of course, there's also oxygen from 0 to -2 is being reduced. So, these are the reactions at the cathode, all the reduction reactions from +1 to 0, from +1 to 0, from 0 to -1. How about the anode? Well, the thiourea could be oxidized and the sulfur could be oxidized. This sulfur is, as you know, in the thiourea. Or you can have bisulfate to sulfate. So these are all possible reactions. And you have to kind of look at these components very rigorously. When you do all that, the encapsulating final conclusion would be that we did see sulfate in the final solution after electrolysis, and it was present at about, let's say, 2 to 3 milligrams per liter, which is not a very high number as you can see. What is the current efficiency? That is a very important parameter, and the current efficiency is kind of low to begin with, only 20%, because what is the current efficiency based on? It's based on how much silver you are able to kind of deposit or transfer, and based on the electron equivalent of current path. But silver is not the only thing that is depositing. There are so many other things going on. So you cannot expect, if you say, well, the process is so inefficient, it's 20% to begin with, it's not a very kind of scientifically sound statement, because silver is not the only thing that you are, only thing that is consuming this current. You do not have any control over this regenerating solution in the sense that silver thiourea complexes. So all I'm trying to say is that if you can get 20% current efficiency, it's not bad. It's not like a student is getting 20 out of 100 in an exam. All right. So, but then you do see a drastic drop in current efficiency. That's the one that one has to look into as you go ahead in time. What does that mean? It means that we have to come up with a technology such that we finish this silver transfer at less than, let's say, 5,000 seconds. All right. So then, when I say we are generating silver nanoparticles, how good is this product? So that morphology is very important. And so you do all these SEM tests, and what you see is that at 60 RPM, so this is 0.05 amps, 60 RPM is A, 300 RPM is B, and 600 RPM is C. At 60 RPM, what you get dendritic crystal agglomerate, which is not something very desired. So dendritic crystal agglomerates, what was their characterization? 1 to 1.5 microns in length, 150 to 250 nanometers diameter at the bottom, and 350 to 400 at the top. When you go to 300, you get closely packed spherical beads, 300 to 1 micron in diameter. When you go to 600, you get uniform. So this word is very critical. Uniform Ag electrode deposit, average diameter of about 320 nanometers. This is what we want, right? And of course, when you say nanoparticles, all of them will not be of one size. There will be a distribution. So this is citric acid stabilization. Citric acid is used as the stabilizer. So what you see are the histogram is very good because it gives us a pretty kind of normal distribution. So you see that the particle diameter now is about median of about. So this is a little different from here because this one was 320 nanometers. Now, when we are able to stabilize it in our second electrolytic cell, and we don't allow it to grow now. So now we can get even smaller nanoparticles, and so we can now get nanoparticles which are about 5 nanometers. What is the difference between this and this? Here we are not stabilizing; we are just. I don't have that, but I mean here we put in the second electrolytic cell and we let the particles agglomerate. Then, of course, it's sequentially pretty high. But if we now stabilize them, we do not let them agglomerate, we can go down to about 6, let's say 6 nanometers median, which is very good. We did a very extensive literature search. No other publication as of today exists which can give you 6 nanoparticles, 6 nanometer diameter particles. Okay. So we are very happy with this result. Some further characterization: UV-based citric acid. How much citric acid? 5 grams per liter. And what is the plasmon absorption speed? 405. And what do we get? We get spherical, which is wonderful. We get monodispersed, which is great. And this is with the nanoparticles that are stabilized with citric. How much time to formation? Little more than 5 minutes. What is the increasing peak intensity with time? Shows increasing AG0 nanoparticle concentration. Symmetric, very important. Broad absorption band indicates smaller size particles with narrow size distribution. This is something that others have also seen, that if you have a broad absorption band and if you have symmetric band, that means your size distribution is narrow. Spherical, as I said, monodispersed, 6 nanometers average diameter and alpha max at 405. And what does it prove? It proves that citric acid is a very good stabilizing agent. So, an earlier question on day 1 was that if I am getting in my system particles that are self-agglomerating, how do I prevent them? You prevent them by using a stabilizing agent. Which stabilizing agent to use? Well, you have a whole range. Then you have to go a little deeper into chemistry. So we tried a bunch of other stabilizing agents as well, because cellulose based and also glucose, but that didn't work, so I'm not showing that. So what I'm saying is that you have to zoom in on the stabilizing agent that's perfect for you. That's the most appropriate for you. In this case, it is citric acid. So 6 nanometers, alpha max at 405, and for 10 grams per liter citric acid, the alpha max gets shift. Possibly higher citric acid concentration promote its reducing behavior. As you know, I mean, citric acid does have some reducing capacity, and we started to see some black electrode deposit when you go more than 90% silver recovery. So to conclude, and this will be my final set of conclusions, we have been able to optimize this process of electrolytic recovery of silver. Silver electrode deposition operation has been fully optimized with current of 0.05 ampere, stirring speed of 600 RPM. We get about 94% silver recovery and only 2% biochemicals. This is first order kinetics, and the constraints are mass transfer and electron transfer. And iurea, that 2% loss that I talked about, that is in that iurea, the sulfur is oxidized to sulfate at the anode. Ag0, nanoparticles are spherical, where they are monodispersed, average particle diameter of about 6 nanometers, and it follows a Gaussian fit very well with the standard deviation of only about 2.6. Citric acid is a good stabilizing agent with plasmon peak intensity at about 4 or 5 nanometers. If I go to higher citric acid concentration, the peak shifts, indicating increase in the particle size. Finally, how well can I reuse the regenerant and the resin? And we have tried, of course, this is a lab environment, we have tried up to 5 cycles. You can say 5 cycles is a very low number, but we do have some limitations in terms of how many cycles we can do in a lab in a reasonably in a reasonable amount of time. So what I can say based on just 5 cycles is that the resin performance is not compromised. The uptake capacity remains at about 300 milligrams of silver per gram of dry resin. And after every cycle, we need a sodium hydroxide wash. That wash is needed because we do form a thin kind of film on this resin, which we need to remove. The regenerant was reused. The drop in regenerant efficiency is due to TU loss during electrolysis, as we just discussed. But it is not a very drastic loss. From 98 to 92 after 4 cycles, it's still pretty good. Because all you have to do is add the remaining, you make up this loss. So at the end of the 4th cycle, sulfate concentration, of course, as you can see, the more you lose, the more sulfate you form. The sulfate concentration is about 20 milligrams per liter, and this validates that DU oxidation is going on till sulfate formation. What are the operating conditions? TU of 0.45 or 0.49 moles per liter. Resin mass, silver loading is about 59 to 61 milligrams. pH of about 1. Sulfate initial is almost 0, and final is about 20. So, what are the key highlights? That we were able to determine what is the distribution of AGTU species, how they affect the regeneration in our back bed column mode. Why did we choose 0.5 molar TU? We have been able to defend that choice. This is perhaps the first work which elaborates in detail the role of detergent chemistry and looks at each component of detergent to see which component affects and which does not. And it is able to recover AG as AG0 and reuse the resin as well as the reagent. We still need to do some more work. Of course, it's not complete research. How contact the packed bed with the influent solution. What is the role of EBCT? As I said, there are some kinetic constraints that we found, but in order to understand it better, we need to change the EBCT of the column and run multiple columns to kind of find that sweet spot. Investigation of different detergent compositions like powder. This is all based on solution. So if you go to powder, there could be, we don't know, I don't know, there could be some differences in the composition. But of course, we have to do a life cycle analysis, which, so I will stop here. So as I said, we can look into these publications and that will give you all the details. If I went very fast, then the details are available in this. So that concludes our course. It's we are a little ahead of time, but I did want to leave some time for feedback from you. I know this has been a very intense 5 days for you, and it has been for me as well. I mean, my gray hair and all that, what it means is that I don't really spend hour after hour in lecture in my academic environment. So here, 3 lectures in a day or 2 lectures plus tutorial is also something which is, I'm coming back to that mode after a long time. So uh, I would like to leave this remaining 10 minutes for Q&A, but more than Q&A, also some feedback from you as to what you think worked, what did not work. And you have to be frank. I mean, there is nothing personal here. So, Upendra, do you want to make some comments?
First, I'd like to thank our professor, Gupta sir, for giving all the, taking such a lot of pain and giving the continuous lecture. So, in a day, 3 hours and again 1.5 hours, 2 hours like that. As sir was telling that the generally professors, senior professors, don't are not that much engaged in so much lectures. So I would like to thank sir from my heart to accepting our invitation and interacting with the students. And you have given very nice lecture notes. I was not getting so much time because I was the single coordinator to hear all your lectures. But what I felt that this is a very advanced course, and normal BTech student will not be able to understand it. And that we have also seen here that initially our BTech students were coming, and then they had left. So in this course, in the Gyan portal, we have seen that around 54 number of students or 56 number of students have registered, but only 25 number of students came, and some of the BTech students were there, so we have not taken them into consideration. And during examination also about 20 students came, and they have written their examination. So I particularly thank the outsider participant, basically from IIT Kharagpur, Vidyasagar University, and from Tezpur, and my research scholars and MTech students who were continuously interacting with our professors, Gupta sir. So thank you for that. And actually, my area is basically adsorption. So my scholars have also done some work in heavy metal removal, and now my students are doing in heavy metal, this dye treatment and all. One student is also doing in CFD. So the slight shifting is also there, because we don't have that much facility over here in children department, and MTech program is also not there. So we have some limitation, but the heavy metal portions they're very nice, particularly ion exchange and chelating agents were there. So I thank you, sir. You have a lot of in-depth knowledge and continuous papers and books you have written. So that is the great contribution. So our India by this course has definitely uh, has been enriched by your lectures, and your notes will be there. And I definitely think that this video lectures would be very helpful. Even though the live stream is also going, some of our professors were also saying this, and they have given some views and all the things I cannot tell you, but they were very much satisfied. And definitely the video lectures that will be kept as a record, and it can be seen later on also. So that is very nice. So wherever you have any problem in understanding, again we can go and again we can see the lectures. And I think we should have more contact with each other, and especially with the professor, so that whatever difficulties you are having or some confusions, that also you can later on can ask and discuss with the sir. Sir will be very busy, and he has very vast areas. In other areas also he is working. So definitely, as we were 5 days together, he will give some time to interact and clear our doubts. And some of you, as I was hearing that they are interested in the higher studies. So I would like to request our sir to give you some how you can go there, and what are the areas where you can go, who are the other persons, and how you can do your PhDs or further studies over there. So thank you, sir. Thank you very much.
Thank you.
So now people can also
Right. We would like to hear from them
yes,
what their experience.
because you are the main person. Yes, you. Now we are only. So we will having a validation session on at 2:30. So I will request everybody to be here at 2:15, so that we can start the right time.
I would like to really thank Professor Shane Gupta for being here and spending significant time with us and explaining all the ion exchange process, because I am not really an ion exchange person. I work on solid based and because Dutch management, but he have also explained like nitrogen recovery, phosphorus recovery. So considering those points only, I have come to this program to understand how resource recovery can be really a new paradigm for India, because as sir have already said that resource recovery is essentially required at the present scenario for global reform. Considering this course, it has been really very good, and I have learned very new things. I would like to thank him for traveling so long and coming here and giving such important time to us. Let's see. I hope everybody here have been benefited by this course, and whatever sir you have taught us it will help us in improving our nation, and we'll try to move to its application part and also seek your help in the due process of time. So I would also like you to share your email IDs and also share some few more contacts, so that contacts of your students, so that in case you are busy, we can consult them also for clarifying our doubts and getting into deeper details. Because since the time was not very much, many deeper details are yet to be disclosed, or like yet to be understood, because all of us will not be so much strong in chemistry. So definitely we will need your help and consultation. Thank you, sir. I would really like to thank you, and I would also like to thank my supervisor, Dr. Shudipta Sharkar, who have been very nice to us and have pushed us a lot to come to this course and contribute to this session. Thank you, sir.
Please don't be shy. I mean, we would also like to know, as Upendraji said, in subsequent Gyan courses, not necessarily with me or him, but subsequent Gyan courses, how we can improve the format and or contents or whatnot. So please be free to express your views.
First, I would like to request that you tell your area of work, what you are doing. Then we can start.
I'm Aparna Datta from IIT Roorkee. I work on treatment of passive mine drainage and recovery of resources under Dr. Sudip Sarkar from Department of Civil Engineering. As I had told during the inaugural function also that my topic is entirely in line with this GAN course. So, like what I thought I have gained from this course, I have learned about various avenues of recovering resources and especially